Welcome back to the second part of our electrostatics notes. Thank you for joining me. If you hear some breathing in the background, it is Hobbs, who is sitting right beside me here as I do this, so ignore the puppy dog as he starts jumping on top of me. What we're going to start with is our electric potential energy. Electric potential energy is defined as UE. Some of y'all might see it as PEE. It's the same thing. And let's talk about what's happening when I bring two positively charged particles together. You know they want to repel each other. So if I take two charged particles and bring them closer together, I have to do work in order for that to happen. Once I do that work, they're going to have some potential energy between them, and the second I let them go, they're going to shoot off. So this UE is going to equal to the negative work. Notice that the signs are opposite because you're going to do work to bring them close together, and then they will shoot off. For those of y'all in the calculus space, you should recognize that quite well. We will, in the next section for my C class, talk about those integrals, but we're not going to worry about it at this time period. Our equation here for potential energy is K, Q1, Q2 over R. Notice that this R is not squared. We don't have to do that, and we just plug it in. And again, that should look very similar to our gravitational potential energy. If you remember, our gravitational potential energy was big G, M1, M2 over R as well. So again, another theme that is replicated. Our K here is going to be 8.99 times 10 to the 9th. Q, of course, is the charge. R is the distance. Our SI unit for energy is the joule. What you need to know here is that energy is not a vector. So put a star, highlight, know all this. You must put the signs in for the charge. So make sure you're putting those signs in as we calculate those charges, and that will enable us to correctly calculate that potential energy here. Bear with me for just a second as I find a calculator, because we're going to have to do some calculations like right now. The potential energy of negative 4.1 times 10 to the minus 2 joules exists between two charges, 6.4 microcoulombs and negative 3.2 microcoulombs. What is the distance between the two? Pretty simple stuff. This is my potential energy, so I'll label that negative 4.1 times 10 to the minus 2. I've got two charges. My Q1 is 6.4. Remember that micro means times 10 to the minus 6. And then I have another Q2 of negative 3.2 times 10 to the minus 6. We're looking for R, the distance between them. Here you go. Plug into the equation here. And as we do so, we're going to have 4.1 times 10 to the minus 2 equals our K, 8.99 times 10 to the 9th, times 6.4 times 10 to the minus 6, times the negative 3.2 times 10 to the minus 6, all of that over R. And again, pretty simple algebra here. At least I hope it's pretty simple algebra for most of y'all. And we're going to plug it into our calculator. And again, I get nervous here because y'all aren't here to correct my stuff. So I'm sure the next day you're going to tell me if I mess any of this up. When I do this math, I get 4.5 meters here. And so that will give us the distance between these two charges. Really simple for potential energy. It's a matter of plugging and chugging into the formula, put in those signs, and get a value. Right now, I want to talk about what a battery is and the purpose of a battery. And so if we look at a battery, we talked about this a little bit last year. I don't know what you remember. Hopefully you know that there are two terminals of the battery. This is a positive terminal. This is a negative terminal. And if it's a AAA battery, it's going to have this 1.5 V associated with it. Hopefully you know that V stands for volts. And so what we can do is we can connect our battery to a light bulb or whatever we're connecting it to and swing it on around. Now, what does this 1.5 volts mean? If you remember from our circuit unit last year, what's going to happen is there's little electrons in this wire. Because it's a metal wire, there's some electrons around with it. And when we plug it in, these electrons are going to start flowing. We're going to produce a current and flow around. So what happens is these electrons, as they leave the battery, have something special about them. These are our special electrons. What they have is they have some electric potential energy. And so as these electrons go through, they have energy, 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 energy. They reach that light bulb. That energy is being converted into, you guessed it, light and heat. And so our energy is converting light and heat. These electrons still continue to flow, but they're no longer special. They have no more energy. And so as they go back around, they go back through the battery. The magic of chemistry happens. They're going to gain that electric potential energy and continue along the path. So, what does that 1.5 volts mean? Basically, what that means is potential, V. This V means potential, electric potential. You're going to see it written a 1,000 different ways. We'll talk about each of those in a minute. But that is the potential energy per unit charge. So that is our definition of volts, the potential energy per unit charge. Now what makes this so difficult is all these name changes. We can't measure potential. Boy, spelled that well. We can't measure potential at all. We don't have a little device that we can stick on and calculate potential. What we can measure, though, is potential difference. And so potential difference is measured with something called a voltmeter. And a voltmeter is able to measure that potential difference. And so when we do this, when this is a 1.5 volt battery, what this means on the positive terminal, it's 1.5 volts, and on the negative terminal, it is 0 volts. So my potential difference is 1.5 volts, which is what the little meter can read. But usually we just say it has a potential of 1.5 volts because most of the time when we read potential difference, one of the measurements is 0. And so when we say calculate the potential, we're really calculating the potential difference. We just get lazy and don't want to do that. If that's all super confusing, don't really worry about it. Just know that when you're measuring potential difference. Okay, I don't like the way this is written here, so we're going to change this out. And so that volts is the potential energy per unit charge. If y'all are more familiar with PEE, it is the same thing. I meant to change that up and I didn't get it done before y'all sent the notes. So the potential is the energy per unit charge. Okay. Q again is the value. The SI unit for the electric potential is the volt. This is what is so bad. We usually don't say, what's the volts? What's the potential? We say, how much voltage does it have? That would just be like saying, what's the force? And you answer newtons. I'm sorry. Yeah, that's just totally messed up. Never mind what I just said. When we do volts, make sure you realize the SI unit is volts. We're asking for what is the potential. Let's work this problem super quickly, see if it's very hard or not. Suppose an electron in TV set is accelerated from rest through a potential difference of 500 volts. What is the change in potential energy of the electron? Okay, let's list our variables. We know the potential is 500 volts. We've got an electron, so hopefully you remember the charge on an electron is 1.6 times 10 to the minus 19 coulombs. And we're looking for our energy. What is our electric potential energy? V is going to equal to the electric potential energy per unit charge. And so the potential energy here is equal to VQ. Again, you need to remember that equation because we'll end up using that a whole heck of a lot here really shortly. But the electric potential is equal to VQ. And so as we calculate this electric potential energy, we'll take our 500 and we'll multiply that by 1.6 times 10 to the minus 19 coulombs. And if I can plug into a calculator, we shall get an electric potential energy equal to 8 times 10 to the minus 17 joules. Not too bad there. Again, equations that you need to remember are here and here. Part B, what is the speed of the electron as a result of this? Okay, how are we going to calculate speed? Speed, speed, speed. If you just calculate energy and you're looking for speed, what should pop into your mind? I know y'all are going to try to use the kinematic equations. That's not the easiest way to do this one. If we're calculating potential energy, conservation of energy is the way to go. And so what we will have is our kinetic energy plus our potential energy is going to equal to our kinetic energy plus our potential energy. You can see that it starts from rest, so my initial kinetic energy is 0. And after the electron hits the TV, it's going to have no potential energy. So we'll end up with 8 times 10 to the minus 17 equals 1/2 mv squared. Alright, can you pull the mass of electron out? Unfortunately, nerdy Miss Hood knows that. 9.11 times 10 to the minus 31 equals that, the mass of that electron, and then we can calculate that velocity.
Bess says hi!
And as you can see, I hope it picked up Bess saying hi. Aren't you excited you get to hear Bess' voice?
Oh.
And so when I do my math, I should get a velocity of 1.5 times 10 to the 15 meters per second. Of course, Beth probably screwed me up and got me off track, so I'm going to do that again as I fill in time here and try to calculate that velocity. Yeah, I got a totally different answer that time, so we're scratching that. And that time I got 1.3 times 10 to the...
Hogs, you can't bark!
And so, if we do this again, to check it a third time, while you get to hear Hobbs bark at me, yep, that's my correct answer there. Alright, so that is another process to do with that. This is another equation that we need to know for electric potential. You can see that potential equals kq over r. Basically what that means, if I have a charged particle, QO, around this charged particle is going to be these equipotential lines. And these equipotential lines are lines where the electric potential is the same throughout the whole area. And so the closer, of course, we are to this charged particle, the higher our electric potential. So this might be 10 volts, 8 volts, 6 volts, and vice versa. So again, those equations should look really familiar to you as we talk about potential and we talk about this. And so you can calculate this and do that. Sorry, Bess handed me a note, so yet again I got sidetracked. Let's work this problem here. We're going to find the electric potential at point P. And so as we worry about potential, when you see potential and potential energy, you think you're lucky stars because this is easy. You can forget about direction for these quantities. Basically, all you're going to do is plug them in. So if I want to calculate the total potential, I'm going to calculate the potential by the first charge plus the potential by the second charge. And I'm going to label this one Q1. I'm going to label this guy Q2. So to calculate the total potential, all I have to do is add them up. So my total potential is going to be KQ1 over R plus KQ2 over R. And so we'll have 8.99 times 10 to the 9th times 4.5, and I got to put that negative in, times 10 to the minus 6 over 4.8. And then I'm going to have my 8.99 times 10 to the 9th times 9.1 times 10 to the minus 6. Uh-oh, what am I going to do for this distance? I don't have it, so I have to use the dreaded Pythagorean theorem. And when I do that, I end up getting 5.6 here, so that will go in that unit. Plugging into our calculator, again, for potential and potential energy, I have to put in those signs. And as I do so, I get an error message on my calculator. Yay! Let's start over again. 8.99 to the 9th times a negative 4.5 to the minus 6 divided by 4.8 plus my next term. This is another time where I need the cheesy physics jokes. Too bad I can't plug into a calculator and do that at the same time. When I got my math, I got 6181 volts here. Hopefully that is the correct answer. I'm going to double check myself as I try to fill in some time here to make sure I'm doing it right. But I think I did. Have you got your college applications done? Hope so. That is correct. 6181 is what I got there, so that is correct. Again, this is a little bit of discussion on electric potential energy. We don't have an instrumentation to measure that, so it's simply the potential between 2 points. This next little page, if you do one thing, I need for you to pay attention to this part right here. This is our formula review of what we've covered so far. This is the box. This is oh so important. What I want you to do is put force up here on the corner. I want you to put field. I want you to put electric field. The symbol that we use for force, of course, Fe. The symbol that we use for the electric field is E. Down here on the bottom, I want you to put electric potential energy. The key word here being energy. Energy, energy, energy. UE or PEE, either one. And then I want on this corner to be the electric potential. For electric potential, we'll use V. Alright, here they are. These equations. You need to know them. You need to know them without sleeping. Without sleeping. You need to know them without thinking. This is F equals K, Q1, Q2 over R squared. Our SI unit here for force, of course, is the Newton. Over here, the electric field. There's going to be two equations that I want you to know here. So I'm going to draw a line here. The electric field is going to be the force that a test charge experiences. It's also equal to KQ over R squared. And again, our SI unit for that electric force is going to be a Newton per Coulomb. Moving on down. For our electric potential energy, K, Q1, Q2 over R. Our SI unit for energy is the joule. Electric potential, V. There's going to be two equations, just like we did before, that I want you to know. V is the potential energy per unit charge. It's also equal to KQ over R. And our SI unit here, of course, is the volt. And the volt, of course, is a joule per Coulomb. I want you to look at these equations. I'm going to see if I can smush this just a little bit so you can see it all on the screenshot, which will just allow me to do that. Look at how these are pretty close. Force is over R squared. Potential energy is over R. I've got two equations here. E equals the force that a test charge experiences. V is potential energy per unit charge. The electric field, KQ over R squared. Potential, KQ over R. Remember last year we did this. We're going to do this again. I want you to put the unhappy faces on these top two. Why are these two unhappy faces? Because they are hard. These are hard. You must do the direction and draw your T-charts. And they get yucky, yucky, yucky. So those are our hard ones. Down here on the bottom, these are our easier ones. Put the little happy faces down here. Because all you have to do is add them up. But remember, these are the stars where you must put in the signs. So make sure you're putting in the signs as we do this. And so that's going to conclude this little section of this next one. We'll come back and talk about uniform electric field after I see what the heck is wrong with Hobbs and why he's barking. We'll be back in just a minute.